Force is a vector, so direction is important. So if there is a, let's say, negative, positive, positive. I alluded to this before. So think about what forces are acting on this charge. Well, you've got a force from this guy, force from this guy. Let me give the numbers. 1, 2, 3. These two are like charges, so they would attract, which would mean that this guy would pull this one this way. So the force between 1 and 2 would pull that guy to the right. And then 3 and 1, they're also like charges, so they would attract. So 3 would tend to pull 1 toward itself. So both forces on that guy would be to the right. And we look at number 2. Force from 1 is going to attract. So 1 would tend to pull 2 toward itself, to the left. Force between 3 and 2, the same sign, so they would repel, which means that charge 3 would tend to push charge 2 to the left. On charge 3, 1 and 3 would attract, so 1 would tend to pull 3 to the left. 2 and 3 would repel, so 2 would tend to push 3 to the right. And then we can double check our reasoning with Newton's third law. Force on 1 from 2, 1 on 2, same magnitude, opposite direction. Okay. Same magnitude, opposite direction, same magnitude, opposite direction. So all of those make sense in accordance with Newton's third law. Okay. We could also think about, in 2D. So we've got positive charges at the top left and bottom right, negative charges at the top right and bottom left. So what is the direction of the net force on a positive charge placed? In the middle. Okay, let's think about that. So positive charge in the middle. Force from this guy will attract. Force from this guy will attract. Force from this guy will repel. Force from this guy will repel. They all have equal magnitudes. They're all the same distance away. So these cancel out, these cancel out. Net force doesn't have a direction. Net force is 0. In the middle of the right side of the square. Okay, well now I've got a positive charge right here. Force from this guy will repel. Force from this guy will attract. Force from this guy will repel. Force from this guy will attract. Alright, well these two are the same distance away. So these two vectors have the same magnitude, they're at the same angle, which means they'll add up to going straight down. These two, of course, are straight up. These two guys are closer. They're going to supply equal force because they're the same magnitude and same distance away from this guy. But these two guys are each closer to our charge than these guys are, which means the magnitude of the force they're exerting is going to be bigger than the magnitude these guys are exerting, which means that the net force will then be upward or toward the top of the square. Okay, in the middle of the top side of the square, similar argument, repel, attract, repel, attract, kind of by the same argument as this one. Force on this guy would be to the right. So you can qualitatively figure those things out. On the AP exam, it doesn't seem like you're going to be asked a 2D calculational question with electric force. So I just am limiting myself to these conceptual sorts of examples. But you may be asked to do vector addition in one dimension. So we've got 1.5 microcoulombs at the origin, negative 2.3 microcoulombs. Oops. At 1.6 centimeters, 0, and at 3.5, 0, at 1.9 microcoulombs. So that's 3.5 centimeters, so quick subtraction tells us that that's 1.9 centimeters. Find the net force on each charge. Well, we can figure this out. So Applying our formula, we know electric force is K Q1 Q2 over R squared. So the magnitude of the force, I'll call those 1, 2, and 3 just for clarity, symbology. The magnitude of the force between 1 and 2 is K times 1.5 times 2.3. Each of those are times 10 to the minus 6. So that's times 10 to the minus 12 over 1.6 centimeters is 0.016 squared. So that's the magnitude of the force between 1 and 2. Magnitude of the force between 1 and 3. K 1.5, 1.9, 10 to the minus 12th over 3.5 centimeters, 0.035. Oops. And between 2 and 3, we've got K 2.3, 1.9 times 10 to the minus 12th over 0.019 squared. So this is the magnitude of the force between each pair of charges. And then, once we have magnitudes, now we just think through it qualitatively like we did with this guy back here. So, positive, negative, positive. Actually, we already did that. It's the same. Oh, no, it's the opposite. Okay, never mind. So we think about, on number 1, what do we have? Well, force from 2 is attractive, so 2 would tend to pull 1 to the right. So we've got force between 1 and 2. 1 and 3 would repel each other, so 3 would tend to push 1 to the left. So if I call the right positive and the left negative, then my net force would be equal to magnitude of F12 minus magnitude of F13. On charge 2, then, well, what's happening? Well, charge 1 would attract it, so that would be a force to the left. So you got the force from 1 to the left, therefore negative. Charge 3 would also attract it, so the force from 3 would act to the right, so that would be plus 2, 3. And then for 3, force from 1 would repel, so that would push it to the right. So positive F13, 2 and 3 would attract, so 2 would pull 3 to the left. So minus 2, 3. So that's how you'd figure it out. And then you could go ahead and calculate numbers if you wanted to. I'm going to pause and then just write the answers real quick. So then calculating those values tells us the force between 1 and 2 is about 121 newtons, 1 and 3, 20.9, 2 and 3, 108, and then adding them together gets us for force 1, comes out to a positive 100 newtons, that's 100 newtons in the plus x direction, and a negative 12.3 newtons means we've got about 12.3 newtons in the minus x direction. Negative 87.9 newtons means we've got negative 87.9 newtons in the minus x direction. Okay. Here's another problem. 4.5 nanocoulombs and 3.6 nanocoulombs placed 4.5 centimeters apart. So 4.5 nanocoulombs, 3.6 nanocoulombs, 4.5 centimeters apart. How far from the 4.5 nanocoulomb charge to the third charge we place so that the net force on it is 0? So we've got an unknown charge being put somewhere, and we want the net force to be 0. So let's think about this. If we put a charge over here, say we put a little positive charge over here, force from this guy would repel, so that would push it to the left. Force from this guy would also repel, so that would push it to the left. Net force cannot be 0 on a charge out here. Over here, the negative charge would be the same. They'd both attract, so they'd both be to the right. Out here, put a little charge. Force from this guy would repel, so it would be to the right. Force from this guy would repel, so the force would be to the right. So we also can't have the charge out here. So the charge has to be somewhere in between the two of them. So let's say we're putting a little charge right here. Say that distance is x. And that makes this 4.5 minus x. And if the net force is 0, then the force from this guy has to be equal and opposite to the force from that guy. They're going to be opposite. We can see that qualitatively in opposite directions. So for them to be equal in magnitude, then we'd have to say K times 4.5 times 10 to the minus 9th times this unknown charge over distance between them, x squared, has to be equal to K times 3.6 nanocoulombs times this unknown charge over 4.5 minus x squared. Or you could change it to 0.045. If I leave it as 4.5, then I'll just get my answer in centimeters. And K goes bye-bye, Q goes bye-bye, and we can actually get rid of the powers of 10 too, and then cross-multiply. So that gives us 4.5 times 4.5 minus x squared equals 3.6 x squared. There are a couple different ways you could solve this. The simplest way is to just square root it at this point. So let's go ahead, let's move this to one side or the other. So 4.5 over 3.6 is 1.25. Take the square root of everything, and that gives us 1.118 times 4.5 minus x equals x. And from there, we're just doing algebra. We distribute that, take that times 4.5, which gives us 5.03 something minus 1.18 x, and then adding that to the other side, then we've got 1 plus that 1.18 stuff. So we've got 5.03 equals 2.118 x. So our x is about 2.38 centimeters. Does this make sense? Let's stop and think. Halfway between these two charges would be 2.25 centimeters. And at that point, which force would be bigger? Well, the distance would be the same, so the bigger charge would exert a bigger force. And look, 2.38, we're farther away there, we're closer to the smaller charge, so that answer then makes sense. Right. The kind of glossed over, this equation is actually quadratic, so if you solve it fully accurately, you'll get two solutions. One of them will always be an answer that is either bigger than 4.5, so we're out here, or less than 0, so we're out here. And that doesn't work because we wrote this equation initially. So our initial equation, we've got a rightward force from this guy and a leftward force from the charge on the right. Adding up to 0, writing Newton's second law. And this being positive, this being negative, is those signs are determined by the fact that we're in between the two charges. So the solution that is negative or bigger than 4.5 is not a valid one. So that's something we can do that's a little bit more algebraically complex. Yeah. You have homework? I'll see you after spring break.